Okay, so it's about projections, and through these computations we have discovered the specific formula for the projection. So that's the definition. You don't have to remember the derivation, which is what right above. Certainly the ideas, however, are very important. The end result is the definition and the theorem. So the meaning of the projection is literally such a special vector that is parallel to what is being projected on, and at the same time the difference between that and the original vector is perpendicular to that vector. So in other words, it is the key idea is still the decomposition. So even though it looks slightly different, but you can see that say what is the I'll put R here. R. Okay. So have a vector X. We have a vector over there, a short one over there. That's my V. Okay. So, and then we decompose P. We found the P is in what sense? In the sense that of the decomposition. So X is equal to V plus R. Okay, not V plus R, CV plus R. CV plus R, so a multiple of V, and plus R, which is perpendicular to V. Okay, so I use slightly different notation with parallel lines and perpendicular, the symbol perpendicular and parallel. But as you can see, it is once you discover that parallel is simply multiple, that makes life easier. Okay, and then the meaning of the R is something that we disregard for whatever reason, or something that we try to minimize that in other situation when this appears, this kind of analysis. But the basic idea, if you want a metaphor for this idea, it is a shadow. Okay, a shadow, as you can see, there is X, some kind of object on standing on the surface, and then right above the surface, the sun throws its rays strictly down, and then what is the shadow of X? Okay, so there is no really surface. That's the limitation of our analysis so far, is that we do not have we don't have even a plane. We have a single vector. So if you're thinking, for example, like computer graphics, then one of the many things that you might need to do is literally compute or pre-compute or compute then, on the spot, compute the shadows of objects. Okay, so and that's just a step in that direction. So like I said, we have only projection of a vector on a vector, and we don't have a projector of a vector on a plane. Why? Because we don't really know what the plane is just yet. So one point I was going to make is crucial to the whole analysis, and it is that the projection of X on V depends only on the direction of V. What does it mean? Depends only on the direction of V. The picture on the right certainly suggests that it is supposed to be the case. It's by design. By design, imagine that in the picture on the right, you double the size of the vector V. What's going to happen? You see the red vector? That's my V on the right. If I double it, what happens?
Which one? It's equal to P.
What?
Is it equal to P?
What is equal to P?
D, if you double it.
What D? There's no D.
P.
There's a P. Okay, so the question is, what's going to happen to P if I double V? What?
Shrinks.
Nothing. The answer is nothing. No, nothing. That's the idea that I try to put here, is that the direction matters. So if you double a vector, or even if you reverse the direction to the opposite, the answer will be still the same. Okay. So which means that well, we are talking about even though not about the projection on a plane, but at least we can understand this as a projection on a line. So on a line on which the vector v lies will be what matters, and it doesn't matter what v is as long as it's not zero. The projection will be always the same. Okay, why it is might be by design. So we solve the problem as it was posed, and as it is defined over there, it suggests that it should be independent of the magnitude. But in the answer, the magnitude appears to be right over there. So it is, however, misleading. We could actually demonstrate that this is not the case. So to demonstrate why it depends only on the direction is this. Well, first of all, what is the direction? That might help. What is the direction? What do we understand? How do we understand directions?
I mean, just the negative and positive?
What?
Just the negative and positive of the...
No, vectors. What is the direction of a given vector? There is a way. We had a construction for that. So a vector and its double and its triple have the same direction.
Just its components?
Well, that would be algebraic. No, the answer is the unit vector.
Oh, okay.
The unit vector, that gives you purely the direction, so you remove the magnitude out of consideration. That's how. So you just divide by the magnitude. So then the direction of v depends on the direction of v. What is it? And the answer is v over v magnitude. That's the unit vector. So magnitude is 1. And then we can just do a little tweak that formula that we have demonstrated at the bottom, and we see that we could actually rearrange things to see only the direction of v. Do you see how? Well, you see that v appears twice, and the magnitude of v also appears twice. Right? So,
Two directions.
what?
Two directions.
What?
Two directions, he said.
Oh, well, okay. So what do you mean?
I mean, we have like v squared over something squared. And it
Right, it's not technically v squared because that over there dot stands for the dot product, so we cannot be as casual about this, unfortunately. By the way, there is no dot before the second v because that is already not dot product, it is scalar product because the fraction is a number. So you have to be very careful, but it's not really hard. Remember, we have the associativity property of scalar multiplication as well as the associativity property of the dot product. So I could simply distribute the denominator over those two v's. So I will have x dot v over v magnitude, that's the unit vector, and then that number is multiplied by what? By vector, which is also the unit vector of v. You see the point? That's been demonstrated. Yeah, so there is no magnitude. It's just the unit vector over here. You remember, that's the technical definition is v over magnitude of v is the unit vector in the direction of v. Okay, so literally the direction. And so it just appears twice in our formula. That's all. Okay, so that's just a bonus. I mean, we knew that it was supposed to happen just by the nature of the problem itself. It had to be independent of the magnitude of v, and we got that. Okay. Okay, so then, like I said, we are not in the position to actually take a good advantage of this formula because even though it looks algebraic, but this you can just plug it into any kind of computer or Excel. and then compute the projections, right? So both the numerator and denominator in that formula for C over here is a dot product. Okay, so if you have coordinates, no matter how many, so 100-dimensional space, you simply carry out 100-dimensional dot product in the numerator, and then the same sum of squares in the denominator, and that's all there is, and you have your answer. But it just you are living in a 100-dimensional space, and yet you can only do projection on a single vector. Okay, so the picture that I had just some time ago about projections, which this. If you want to have a projection of a vector A on the plane, then you have to look at the projection on every single vector in that plane. Not a single, but all of them, and they point in all possible directions. So that's the missing part. We don't really have enough room to do these constructions on. So we just lack some geometric entities on which, say, such as planes, in order to deal with this kind of nice formula to make it applicable. So the point is that we got to move to the next level, and that is functions. Predictably, functions. We cannot really do anything without functions. We limit ourselves to linear functions, of course, but the dimensions go straight up. So functions between they are linear. And they were, well, to be explained what that means, between Euclidean spaces. So generally, we have function f from Rn to Rm. So that's the standard notation for what we're going to be concerned with. So this is being the domain, the inputs. This is the codomain, outputs. So linear is the last problem for our to figure out what it means. We'll start with examples. We need a lot because at this point the only familiar from pre-calculus and calculus is n is equal to 1 and m is equal to 1. So that is very limiting. That is very limiting, and as you remember, so f of x is equal to mx is our only linear function that we have available. And you can see how much room we have in terms of the dimensions, and then how little functions, how few functions we know. Okay, so well, so let me first have a little table here to show you where we're gonna end up. So if I put here dimension of, well, I'll put n here. So dimension of the input here, dimension of output there. So 1, 2, 3, 1, 2, 3. So it's a whole table of possible classes of functions. So both of these are dimensions, but dimensions, so this is m and n, but dimensions are for the domain and codomain. So, and then turns out we are only familiar with this. Okay, so input one-dimensional, output one-dimensional. Both are numerical. Okay, so then at least we have to progress from this on to the left and to the right, at least. And I put a question mark here. We're not gonna worry about it for a little while, but these are we gonna go this way and then that way. So in other words, input is one-dimensional. That's the number one step up. Input one-dimensional, output will be two-dimensional and higher. So going from this initial cell vertically or horizontally will be the easiest. Okay, but then we'll have to go diagonally sooner or later. Okay, so once again we're starting with, this is where we're gonna be working in that cell, this cell. Okay, the difference is not huge just yet. Not huge. If I just, let me just try to visualize what we're talking about. The output is different, two-dimensional versus one-dimensional, and well, I'm just plotting my function, right? Y equal mx. I hope this one is passing through the origin as intended. And now the way to visualize these, the vector valued, this is vector valued function this time, not numerical as we're used to, okay, which might look very similar. I'm looking at, well, that's what it looks like. It looks exactly the same visualization. But the only reason is that it is the difference between the graph and the image. So I visualize the graph of the numerical function in the first cell, and in the second cell I visualize the image. Why? Because just the reason is that we want to keep the dimensions as low as possible. So as you start climbing dimensions, there's less and less room. So it pays to drop one of the dimensions and hide it. So in this particular case, I'm hiding what am I hiding? I'm hiding the input variable, input dimension. So those two axes that you see in the second cell are both the output dimensions, and the input dimension is hidden. So the way to understand it is through motion. So the variable of the input might be simply time, and you're moving. That's the main difference between the two pictures. That when you're moving through the plane along a straight line, you have to indicate the direction. Okay, so that is one difference. The other difference is that there cannot be no vertical lines. In the first cell, you cannot have vertical lines because it's not a function. But you can certainly move through a plane vertically. It doesn't make any difference. Any direction works. So let me expand this. So this is once again y equal mx, or let me y equal mx. Okay, so x and y. So as you can see, this is the input. This is the output. It's very straightforward. And now if we are moving on, the input is still one-dimensional, but the output is now two-dimensional. What do? I need how many dimensions? I need 3. Now I have technically 3 variables for the input, output, and 2 for the output. So I still can handle that. It just makes things hard. So let me try. Like this. So I'm using my 3-dimensional space, x, y, and this one is just traditional, is called t. So that is the input variable. So in other words, just as the y-axis was the output, right? The output was y. Now the output is the whole xy plane. Okay. Input. Input is still one-dimensional, but the output has become two-dimensional. And as you can see, the whole situation becomes three-dimensional. So how does it work out? For every, the rule still works the same way. For every t, there is only one output. So except in the first case, it was a number, and that's how we plot it, right? So that's an x given. I carry out computation, and I have the output value over there, f of x, and I plot it point by point. That's the graph. This is also the graph, and it works exactly the same way. For every x, I will, through some computation, I will find what? 2 y and x, which if you want to stick with vector notation, will be simply a vector like this. or a point, a vector doesn't really matter, but it lies within the xy plane. So this is the input, that is a t now. T input is here on the horizontal plane, horizontal line, and the output is anything on the vertical plane, the blue one. Okay, so I can still plot this vector over here somewhere, say maybe like this. So if I really want to plot the graph, I will have to associate one with the other. Okay, so that's the procedure for how to get from t to, that's messy, how to get from t to, what is it, f of t. So this is t, and this vector over there is f of t. The only question is what becomes of, what does the graph look like? And the answer is it's still going to be a curve. Specifically, if we stick with linearity, which will be a straight line. So, okay, except it lies in the three-dimensional space. That line lies in the three-dimensional space. Okay, so the question now, what does it have to do with the with that picture on the second cell over there? So what happens if I drop the dimension 3? I'm sorry, the third dimension, the input variable, the x-axis, the t-axis. So I keep x and y, okay, and then what do I do to that orange line? No, close, but no. Project it. I will project it on the xy plane, and then so that way we are not, what you're looking at the top is the space-time, and I want to look at space. Period. Okay, so like this. So it will look like this. So there's no t-axis, and we're left with only the image. So that's what image is called, as opposed to the graph. There's the for every function there is a graph, which lies in this particular case in three-dimensional space, and there is its image, which lies in the target space. Okay, and it's so one-dimensional lower. Especially for linear case, it's sometimes sufficient as far as the realizing what's going on. I forgot to add, this is maybe a way to differentiate the picture on the left and the picture at the bottom, is that you have to indicate the direction, because you can have the same image with different graphs. So it's once again, if you want a metaphor, it's motion, and you can travel the same path at different speeds and in different directions. Okay, so that path over there, that image of the path of our motion comes from that graph at the top right, but you could think of different ways to travel it. So not a big deal, because this is entirely about visualization, but on the other hand, we got to try to visualize as much as possible for as long as we stay in lower dimensions. We go to high dimensions, we cannot visualize, and there is only resort is algebra. So we better use our eyes for as long as we can, because then at some point we can't anymore. So and this is the progress that we make. This progress is dimension 1 to dimension 2, and then we're going to do this many times. And the transition is actually what matters. And so that imagine how we can go on in the same manner, higher dimension, one at a time. So like I said, it's still visualization, but the concepts that come up here are crucial. And so let me define them, and that is the two concepts are the graph and the image. Okay, so starting with f of x, f from Rn to Rm, once again, the graph, so the graph of f is the set of all x, y. And now the tricky part is where it lies. the graph contains all the information about the function because it has all the x's inputs as well as the corresponding outputs. So with y equal f of x. Okay, so as you can see, I'm using this notation to take care of all possible dimensions. So x is a vector in Rn, y is a vector in Rm. Okay? And then what I do is I have created pairs of x, y. Where do they lie? Where do they lie? What's the space?
Euclidean space?
It will be Euclidean. What's the dimension? What? Look at the example on the right.
3.
It is 3, where n is equal to 1 and m is equal to 2. And the space, the graph lies in what space? Three-dimensional space. So how did we get it? How do we get 3 from 2 and 1?
Is it n plus m?
N plus m, yes. Well, imagine that x has n numbers, string of n numbers, and y is string of m numbers. So if I put them together, I have a string of n plus m numbers. Okay, so that's why it lies in n plus m space. So the easiest one, that's how we end up with a plane. It is 1 and 1, and you have plane two-dimensional. So that's the definition, and we're gonna see many examples of this and and we're gonna become more comfortable with that idea gradually. I just want to have it early on. So I put it next to the definition of the image, which is almost the same thing, only it involves only y's and no x's. So once again, f from Rn to Rm, the image of f is the set of all y's with y equal f of x. Once again, x in Rn, y in Rm. So only the outputs matter. So it's a subset of Rm. So once again, look at the last picture. Last picture, this is the target space or output space. And it happens to be R2, which is m is equal to 2. I'm dropping out of all the inputs, and I'm left with only dimension 2. Okay? So once again, it is a complex concept that only really learned through examples, and we'll gradually go with higher and higher dimensions, more and more complex functions, and then we'll be coming back to these two definitions often. At this time, all I want to do is just to study lines on the plane. And as you can see, we already have guessed that both the graph is a straight line in R3, and the image is also a straight line in R2. Okay, so lines on the plane. So I don't want to do y equal mx anymore because it is it really takes us back, and remember it excludes the vertical lines to begin with, and we want to use the function that we just introduced, a function from R to R2. This is what we want to use for representing lines. Okay, so I pick a line, and I'm interested in once again. So the question is represent this line as the image of such f. So remember, metaphors are good sometimes up to a point, and once again, metaphor is motion. So the hidden variable is t time, and we're simply moving through it. That is certainly our choice. If all you have is a straight line, then there is nothing you can say. You can move it in different ways, but we just pick one. So we have a line, and let's just think of how we represent it how can we move through it. The question is, if you go back to geometry or Euclidean geometry, Euclidean of Euclid, that is the original Euclidean geometry, then a line on a plane, forget about the Cartesian system, you have a piece of paper and you have a line. The line is determined by 2 points. 2 points give you the line. Any 2 distinct points give you a line. Okay. Okay. So where does it? How does that help? It does help us if we interpret the difference of the 2 points as a vector. So that's what we bring to Euclidean geometry from vector algebra. There are vectors. So if there are 2 points, so any 2 points, we're not going to be saying that they determine a line. We'll say distinct. Determine a vector. So P and Q, and then we have PQ, the vector. Well, you can certainly remember what the, say, P1, Pn, Q1, Qn, and then the vector will be simply Q1 minus P1, and so on. Qn minus Pn. So that is the construction of that connects the geometry of points, once again Euclidean, and the vector algebra. 2 points determine a vector in that manner, very predictable way. 2 points. What do? Draw a vector from P to Q. Direction matters, right? And then if you want to also do the coordinates, then this is how we can do it, right? So list of coordinates, list of coordinates for P, list of coordinates for Q, subtract coordinate-wise, and you have your components of your vector, PQ, right? So that's the idea that gives you everything else, because all you need is 2 points. All you need is 2 points in order to determine a line, which means that the conclusion that we make from what Euclid told us in this analysis is that a point and a vector determine a line. A point and a vector. So one vector is not enough, because that way we can have many lines with the same vector. It's called the direction vector. But if you also have a point, then you're fine, right? Okay, so that's what we've got here. Determine a line. That's the plan. This is the plan of finding that function f that we're after by fixing a point and a vector. So if once again I want to interpret this in terms of motion, then an interpretation that that I want to have. So do it this way. So interpretation. The point is the initial location. And the vector, what do you think the vector is? It is the direction, yeah, but if in terms of motion there is something missing. You can even be more specific than the direction. What I'm driving at is the velocity.
Oh, okay.
Right, because you want to know how fast you're going. So that way we have velocity contains both the direction and the speed. Okay, so just one number, one vector instead of having two, one vector and a number. Okay, so and then you can just take this interpretation all the way through and come up with a formula. So a point, say p, and the vector that stands for velocity is v. So then let's find our path. So find the path. Initial location is p, velocity is v. What points have we visited in the end of the day? So the path is the same as the image. In other words, all the points we visit or have visited possibly in the past. Supposedly we started in the beginning of time, and then we'll keep doing it till the end of time. Okay, so so any points that we have visited that you already know? The initial point. Okay, can you think of any other?
Q.
No, there's no Q anymore.
Final.
What?
Final.
What?
Final.
No, there's no final point because, like I said, well, I don't think there is. Until the end of time, we're going to be moving forever, and we have been moving forever.
So there's like an infinite amount of like.
There will be infinitely many locations, obviously, but you can. The easiest one to think of, if suppose you were walking 5 miles an hour from point, where are you after an hour? So where is it? I started at P and I'm moving for an hour in the direction of V. Where am I?
P plus five.
P plus V, right. So P, then P plus V, and then you can certainly probably, after 2 hours, that's where you are, and 3V, and then if you want to move backwards, you can do that too. Well, not backwards, rather backwards in time, all of these as well, right? And then what if I have moved for half an hour? Or 1/10 of an hour. Okay, so in other words, the two fixed parameters p and v is 1, and the input variable is, as we have been talking about, is time. So for each moment of time, there will be a location different from any of the previous locations. So for each t, we are at p plus tv. Okay, so graph certainly is in order here. If I'm at p, and the vector v is it actually starts at the origin. So if I want to really visualize it, I would do it this way. So I put origin here, O, and I put v here. So in order to actually visualize what's happening, I have to repeat the vector v, reattach it to p. That's what this means. So this is still v, except it's moved, and then the next point is p plus v. This is certainly is p plus v. P plus V, but then I keep doing it, and that's what creates a whole line. So in other words, it's I'm talking about the multiples of V. Yes, multiples of V. Any multiple of V is what we need to. It is the how far we went, right? How far we've gone since we were at point P, forward or backwards. Okay, so well, if this is not quite yet there, let's make a picture. Well, say P is equal to, say, 0.12, and V is 2, 3. Okay, so, well, that little that we need to know about motion is really will be sufficient. So 1, 2. So our initial position P is here. Okay, and then we're moving 2, 3 at a time. So I'll move like this. So this is 1, 3. So my vector is, I don't want to plot it on the same spot, same axis, but 1, 2, 3. So this is where I am. In a way, I'm finding the second point, that's all. So this is my vector V, 2, 3. Look at the coordinates. They are 2 and 3, components of this vector 2 and 3. And that way I find another location for us. Well, think of it, that little we know, what a sentence I didn't finish, that little we know about motion is that it is independent of the two coordinates. So you can trace entirely your motion east-west, and you can separately, you can trace your motion north-south, okay? And that's what those coordinates are. So the easiest one is to say x-coordinate is 1 plus 2t, and y is 2 plus 3t. Okay, so once again, horizontal motion and vertical. Well, I mean, vertical and horizontal are only relative to that piece of paper that is hanging vertically, but you can think of xy plane being entirely horizontally and moving through the plane. Except in linear algebra, we don't make any terms. We keep straight. Okay, so that's what we're seeing here. Straight line and initial point, a vector, and then you can build as many as necessary of these points, and it forms a straight line. So this is straight line, and that straight line, it does not pass through the origin, so that's why we need to have extra precautions. But so this is a coordinate-wise representation, which is in comparison to what we just had, which was what is x capital is equal to 1, 2 plus t times 2, 3. Okay, so coordinate-wise or vector-wise. So either you look at x and y separately, or you look at them together as vectors. So either you do numerical algebra twice, right, those two lines, or you do vector algebra once. Which one is better? I think I hope to convince you that vector algebra is better, okay? Especially when you go to higher and higher dimensions, then this P plus TV representation is fully applicable to any dimension, right? That's the power of algebra, of vector algebra. You don't have to worry about how many dimensions behind each of these two vectors P and V. It works out. Okay, so the technical terminology is V is in that representation. So f of t is equal to P plus TV, where P is in Rn. Rm actually, the way we did it, and V is in Rm too, only it is a vector. It's called the direction vector. I mean, if you step away from the metaphor of motion, then where v stands for the velocity, then you think of this as the direction vector, or the direction vector of this particular function. Even though, remember once again, you might have different representations of the same line with different choice of p and v. Well, let's examine that. Take a look at the picture that we already have with this p and v. Can you think of any other representation? Okay, suggest one. How about q equal to what? Yeah, so with the p plus v, so it's 3 and 5, right? 3, 5. Okay, so indeed, I could start the same way. It's like 1 hour into the future, and that I just change the initial point to a different one, and that's it. There's no trouble whatsoever. So that's with the same v, which is 2, 3. Well, I need to use here appropriate notation. Can we change the velocity? So I'll choose p. I'll keep p as 1, 2. What can I do to the direction vector? I can multiply by any number, any except for 0. Except for 0, say how about 4 and 6? Right? Or anything else. Any non-zero multiple of v. Yes. Yeah. So you say it is a straight path. So there's infinitely many ways to follow it. Fast, slow, including in the opposite direction. That's if your multiple is negative, that you're moving in the opposite direction. In the meantime, how would you? So as you can see, I have taken care of all possible direction vectors by this description. I could replace v with any non-zero multiple of v. So that's the second line. What about the first line? What is how free are we as far as q is concerned? As far as p is concerned, let me put here p. So what p could I choose? I choose 1, 2, then we chose 3, 5. What's so special about this pair? Nothing really. What others can you think of?
7, 11.
Yeah, more. The direction is, suppose the velocity is the same.
What is it?
The velocity is the same. Where else can you start with the same velocity so that you will trace the same path? What? Anywhere? Where?
The 1 minus, is it 1 minus x has to be the same?
Right, in other words, you can start at any point on that road. If velocity follows the road, you can start at any point and you will follow. You won't deviate from the road. So any point on the line. So any point on the line. So line is given, then you can represent the same line in a number of ways, and you can vary the direction vector by non-zero multiple, or you can vary the initial point by as long as it stays on the line. Any point on the line. Okay, so we'll just resume next time.